Good morning, SPH3U. It's Mr. LaRusso here. We're still continuing on with dynamics, and we're approaching the end, and we're looking at specifically these higher order universal gravity questions. We're going to start off with questions 1 and 2. Question 3 is slightly different than 1 and 2, and it's, as you can see, affectionately referred to as the dream crusher. You'll see why momentarily, but we're going to focus on questions 1 and 2 first. So let's take a look at question number 1. An astronaut travels to a strange new planet. She is trying to determine some of the properties of the planet. She brought with her a scale from Earth that is calibrated to Earth's gravitational field. Now, this is a very important part of the question here. Specifically, the scale is calibrated to Earth's gravitational field. That's an important point. On Earth, the mass of her and her suit is a total of 100 kilograms. On the new planet, the scale reads a mass of 75 kilograms. Determine what must be the gravitational field strength of the new planet. So what we're looking for is we're trying to figure out what the gravitational field strength of this new planet is. And what I mean by that is I'm looking for the G of that planet. That's what we're looking for. Now on Earth, we know that G has a value of 9.8. So let's take a look at what we got going on here, given. So first of all, we know that her actual mass, so let's call this MR for mass real, is 100 kilograms. But the mass that the scale is reading, let's call that mass apparent, is 75 kilograms. Now we know that she has a mass of 100 kilograms, but on this planet, the scale appears to say only 75 kilograms. Well, we're going to explain why that is in a moment. Now, let's talk about G on Earth. We know that that value is 9.8 meters per second squared. And what we're looking for is the little g of that planet. All right, well, a few things. We know that the force of gravity equation in this case is little m times g. Little m represents the mass of our astronaut, where little g represents the gravitational field strength on whatever planet we're on. If it's on Earth, it's 9.8. If it's on our mystery planet, it's some value that we actually have to solve for. Okay, so how do we actually go about doing this? Well, the thing is to remember that a scale really is something that measures the force of gravity. It's not really measuring your mass. What it's doing is measuring your force of gravity, and the scale on the scale itself, the numbers on the scales are calibrated for a little g of 9.8. So they've actually done this little bit of conversion for you. So what we have to do is, first of all, is find out what the force of gravity our astronaut is actually experiencing on the planet. So we have to find the force of gravity that she is experiencing on the planet. All right, well, here's the thing, is that the scale that we are using, right, is configured for the Earth. So what we've got is the force of gravity on this planet is equal to that mass apparent, because here's the thing, the scale doesn't know that it's on another planet. All it knows is that it feels what 75 kilograms would feel like on Earth. It doesn't matter that she actually has a mass of 100 kilograms. It's how hard her gravitational force is pushing down on the scale. So the scale is just assuming that it's on Earth. So it is giving the reading of a mass of 75 kilograms because it feels a force of gravity that would be equivalent to what 75 kilograms on Earth would produce. So we have to multiply this by G on Earth because this is what the scale is configured for. So 75 kilograms times 9.8, that is 735 newtons. So now that we have that, we can actually truly find the gravitational field strength on that planet. So let's go with this. So what we have is we're going to find G on that planet. Well, to do that, I know that the force of gravity on that planet is equal to the real mass times G of that planet. So rearranging the equation, we get FGP over the real mass. So on this planet, our astronaut is only producing 735 newtons of force of gravity. And her combined mass with her and her suit is actually legitimately 100 kilograms. This means that the acceleration due to gravity on this planet is 7.35 meters per second squared as opposed to 9.8 meters per second squared on Earth. And the shortcut way that you could actually see this is if you take 75% of her, because her mass reading was 75% of the actual mass. So what is 75% of 9.8? You guessed it, 7.35 meters per second squared. This is the mathematical proof to explain why we can simply take 75% of the 9.8. So once you see that, hopefully that makes a little bit more sense than the way the question was initially worded. Now let's take a look at part 2. In part 2, the planet has a radius 2/3 that of Earth's. What is the planet's mass? All right, so in order to do this question, we need to look up what the value for Earth's radius is. And that was shown in previous questions, but the Earth's radius is 6.371009 times 10 to the 6 meters per second squared. The little g on our planet we have just found to be 7.35 meters per second squared. What we've asked to find is the mass of our planet. Well, the formula we're going to use is little g is equal to big G, big M over r squared. Solution. So g is equal to big G, big M over r squared, and we'll add the subscript p's. So isolating for m, we get mp is equal to g subscript p times the radius of our planet squared divided by big G. However, this planet is 2/3 of Earth's radius. So now we can substitute our values in. 7.35, 2/3 of 6.371009 times 10 to the 6 divided by what I call the pizza constant, which is 6.67 times 10 to the negative 11. And let's not forget to square that value, and also make sure we have the appropriate number of brackets. And we get a value of 1.98 times 10 to the 24 kilograms. All right, so now on to question number 3, which I have again called the Dream Crusher. So now our same astronaut travels to a new planet. On this planet, she does some further tests. The first test was to determine the acceleration due to gravity. During this test, she drops a stone from a height of 2 meters, and the average fall time of the stone was 0.755929 seconds. Step 1 is we're trying to determine the acceleration due to gravity. All right, well, let's take a look. We have been given the initial height of this projectile. We also know that the time it takes to fall is 0.755929 seconds. Well, in order to solve this problem, we need to actually get some specific data here. So let's take a look. Now, we're trying to find the little g of the planet, which is also just the acceleration of that planet. Well, acceleration can be found using either kinematics or dynamics. Well, here's the thing. We've been given some information. First of all, we know that the stone has been dropped 2 meters from a height of 2 meters. So that means its displacement. I was going to say it's displacement of the y, but we're just using the y component. We don't have any other components, so we can just use d, is equal to negative 2 meters. That's how far it fell. We also know that the amount of time it took was 0.755929 seconds. Unfortunately, that is only 2 kinematic pieces of information. We need 3. Well, there's one other value, and the key word is that the projectile was dropped. This means that the initial velocity or initial speed is 0 meters per second. All right, so now we have 3 of the 5 possible kinematic parameters. So since we are looking for acceleration, we need a formula that has d, t, v1, and acceleration. And that formula is our very first formula of our accelerated motion problems, and that is d is equal to v1t plus 1/2 at squared. All right, so here's what we got. So our solution to this problem is as follows. We know that d is equal to v1t plus 1/2 at squared. Now, of course, I would have given you grief had you not put a title, so I decided to put a title in. This v1t, it goes to 0 because the initial speed is 0. So now we need to isolate for the acceleration. So to get the acceleration by itself, we have to multiply both sides by 2, divide by t squared, and that gives us our acceleration. So our distance was negative 2 meters, and our time 0.755929 all squared. And when you do this, that should work out to negative 7.00 to 3 sig figs meters per second squared. So the acceleration due to gravity on our planet here, our little g, is just 7.00 meters per second squared. Notice, no negative for the g value. It's just an absolute value. All right, so that is part A. Now, here's where things get a little interesting. Her next test was to determine the mass of the planet. her first step was to determine the radius of the planet, and she did so by placing a spike in the ground and measuring the angle of the shadow at noon. She then traveled 157.08 kilometers north and performed the same experiment. Here are the results. Now let's get the the diagram's missing here. So let's find that diagram. Okay, and there you go. So when she placed the first stick in the ground at noon, the rays of the sunshine were moving in this direction here. So the stick here is blocking the light. So this is what I'm referring to as the shadow angle. So here is the shadow, and then the light picks up here again. So over here, the shadow angle is a bit bigger. So that is going to have a longer shadow. So at the same time of day, further north, the shadow's a little bit longer. All right, well, what is the cause of this? Well, the interesting thing about this is this was discovered by a Greek philosopher mathematician living in Egypt and several years before the birth of Christ by the name of Eratosthenes. And he actually was the first person in history to make an approximation for the size of the planet. This is a remarkable feat. And I will do my best to explain the concept of how he came to this particular determination. So to do that, I'm going to have to switch programs. I'm going to swap over to Google Diagrams. Okay, so back in the time of Eratosthenes, he was living in a city of Alexandria. He heard reports that in a city to the south called Cyan, which I think is modern-day Aswan, that on the first day of the summer solstice at high noon, columns did not produce any shadows and you could see directly down into wells. What Eratosthenes thought was very peculiar is that this particular phenomena did not occur where he lived in Alexandria on the same day. Now, the curiosity that he had was, well, there's one of two possibilities. One, the report was inaccurate, but that didn't make a lot of sense because it's a fairly easy observation, and it would be unlikely that many people would get the observation wrong, or there was some other phenomena occurring. Now, at that time, it was believed that the Earth was flat. So here's the argument. If we have a flat Earth, and even in that time, they knew that the rays of light coming from the sun were essentially parallel. So the argument is this: if the ground is flat and you place a stick in the ground at any point, the shadow angle should be the same. So effectively, we get a triangle that represents the shadow. Well, if we take the same triangle, if the Earth is flat, then the triangle size should be the same each time. So simply moving them back and forth, right, we have similar triangles here. And that means that this shadow angle in here, this angle, which we are referring to as the shadow angle, should be the same for each stick at every location at the same time of day all across the world. But that's not what occurred. So what Eratosthenes realized is that the only explanation, if these rays of light are parallel, is that the surface of the planet itself is curved. And this is a remarkable insight for somebody who had no technological means of making an observation to see the curvature of the Earth. This was implied based on this particular evidence. And it's a remarkable thing that people are still arguing about this today when this observation was made almost 3,000 years ago. So we're going to take a look at how we can use this information to determine what the size of the planet is. So now the next step is I'm going to erase all this and I'm going to make a curved Earth. So here we have our curved planet. Next step is we're going to find the center of the planet. And to do that, we can hover over top and there is the center of the planet. So next thing I'm going to do is I'm going to draw a line from the center of the planet to the equator. Next, what I'm going to do is I'm going to draw some parallel lines that represent the sun's rays hitting the planet at different points. So if we notice at the equator here, the ray of light is coming perfectly perpendicular to the surface at the equator. But as we move up towards the poles, we can see that the ray of light is getting closer to the horizon. And if you're right on the North Pole here, that ray of light would be perfectly horizontal. This actually represents the first day of spring. On the first day of spring, the sun is directly over top of the equator. And as a result, if you're on the North Pole in those polar regions, this is the first time that the sun breaks the horizon. So this is the end of the 6 months of darkness. So I'm just gonna make a few adjustments here to get these rays of light a little bit more parallel. All right, so now the next step. What we're going to do is we're gonna place the stick on the ground. All right, so our first stick, where she places it, was somewhere on the surface. Now, what I'm going to do is I'm going to make my stick extra long. Now, obviously, this would be like 10 times the size of Mount Everest. But for the sake of being able to observe it easily, I am going to make this a little bit on the larger side. And I think I may expand the diagram a bit too. All right, so we've expanded the diagram a little bit. All right, so here is our first stick. Then she places another stick straight in the ground. Now that stick is going to be pointing towards the center of the planet. So I'm just extending the length of the stick to go to the center of the planet. All right, so let's focus on our first stick here again. Get it right up to that ray of light. All right, so let's take a look what's going on. So that first shadow angle that she is referring to, that's this. And this angle right here, this is our theta 1. The shadow would be on the ground here, and this is the stick blocking the light. So here would be darkness. All right, so now she's moved another 157.08 kilometers north. Obviously on the scale of my diagram, I've exaggerated a little bit for ease of for our viewing, but you get the same idea. So next, this is the second shadow angle, and this would be our theta 2. All right, so now that's theta 1, we've got theta 2. So if we take a look down here, we can see some geometry patterns. What you can see here is a Z pattern. So what we know is then that this section right here is also our theta 2, my apologies, theta 1, and that section there, that is our theta 2. So what that means is this little section here, this we're going to call our delta, or delta theta. All right. So now the next little bit of information is that we know that she drove 157.8 kilometers. So the distance between these two sticks is 157.08 kilometers. So this little section highlighted in green, that's our distance. All right, so now here is the next important concept. And what we're going to do is we're going to take this diagram and we're going to bring it over into OneNote. All right, here we are back in OneNote. So the next concept. So we're trying to find the radius of the planet. Well, we need to understand a couple of things. One, what is the relationship between this change in angle and this distance d? Believe it or not, you already actually know this relationship. You just don't realize that you know it yet. So if I was to take just a regular circle and then I was to break it up into quarters like this, what you already know is that in this angle here, in this quarter, that represents 90 degrees. And this distance here along the arc here, that distance you know is equal to 1/4 of the circumference of the whole circle, because this is 1/4 of a circle, so this represents 1/4 of the total distance around. All right, well, what you actually realize is the following idea, is that the ratio of the distance over this change in angle, which is 90 degrees, is equal to the whole circumference divided by 360 degrees, which is the total angle of a circle. Well, if we isolate for d, I get delta theta times c over 360 degrees. Well, delta theta is 90 degrees over 360 degrees. Well, if you reduce this, 90 degrees over 360 degrees, that's just equal to 1/4 of our circumference, which is exactly what we expect. But this works for any angle. So the relationship between this distance d and this angle theta is in the same ratio as the total circumference of the circle compared to 360 degrees. And this is actually how Eratosthenes figured out how big the Earth was. Here's what he did, is he hired somebody to walk the distance from Alexandria all the way down to Syene. And that was 800 kilometers that this person had to walk by foot. And he literally had to calculate and count his footsteps the entire journey. Now imagine that task, that you are walking from equivalent distance of London to Montreal and having to count every step that you took and report that back when you return to Alexandria months later. And based on the observation, that's the only observation that he needed someone else to do. He needed that distance d. This observation he was able to do because when he was in, the folks that were in Syene, they were experiencing this. So he knew that the shadow angle in Syene was 0 degrees, not a problem. All he had to do was measure his own angle and get that distance. And then when he did that, he got an approximation for the Earth's circumference, which is shockingly close to what it actually is. And he got about 40,000 kilometers, which is remarkable, considering he did this based on some dude walking from Alexandria to Syene. All right, so let's actually apply this to our particular calculation. All right, so now what we want to do is we're trying to find the radius of the planet. So I know that d over delta theta is equal to c over 360 degrees. But the circumference of a circle is 2 pi times the radius. All right, so we've got d over delta theta is equal to 2 pi r over 360 degrees. Now we isolate for r. So that's going to be 360 degrees times the distance divided by 2 pi times our delta theta, and that is equal to our r. Substituting in 360 degrees times. Now, here's the thing. That distance is 157.08 kilometers, but those are the wrong units. We have to multiply by 1,000. So first thing I'm going to do is I'm going to put this in scientific notation, which is 1.5708 times 10 to the 2 kilometers. Multiplying by 1,000, that's the equivalent of multiplying by 10 to the 3. So 10 to the 2 times 10 to the 3, you just add the exponents, and we get 1.5708 times 10 to the 5 meters. Substituting that value in, 1.5708 times 10 to the 5 divided by 2 pi, and our delta theta is 35 minus 32, which gives us 4,510,000 meters, which is equal to 4.50, rounding off to the appropriate number of sig figs, times 10 to the 6 meters. So that is the radius of our planet. All right, so next step. Now that we have the radius of the planet, we have to determine what the mass of the planet is. So to find the mass of the planet, we know that little g is equal to big G, big M over r squared. So that's the little g of the planet, mass of the planet, and the radius of the planet. Well, just as a reminder, earlier we found the little g of the planet to be 7.00 meters per second squared. We found the radius of our planet to be 4.50 times 10 to the 6 meters. So now all we have to do is isolate for that. So multiplying both sides by rp squared, and then divided by big G, turning the equation around, and now substituting in. And we get a grand total of 2.12 times 10 to the 24 kilograms. And that, ladies and gentlemen, is how you can determine the radius and the mass of a planet by walking and dropping a rock.